Okay, so 4.3 focuses on complex zeros. So the first thing we need to talk about is what is the definition of a conjugate. So a conjugate, the conjugate pair theorem says that let f of x be a polynomial function whose coefficients are real numbers. So if you have a root that is r equals a plus bi, if that is a zero, then r equals a minus bi is also a zero. So to put it in simple terms, complex numbers always come in pairs. Okay, so if you have a plus bi, then you will also have a minus bi. So let's go ahead and look at these four roots and identify what our conjugates would be. First one, a. If I have a solution 3 plus 2i, because of that theorem, I know that I also have a solution 3 minus 2i, because that is the conjugate. For b, if I have negative 4 minus I, then I also have negative 4 plus I. Notice that when I'm writing the conjugate, I'm only changing that middle sign. For question C, there's an invisible 0 right here. So the conjugate would be 0 plus 2i, or just 2i. And for the last one, the conjugate would be negative 3 minus 5i. So we're going to use that as we find the remaining zeros of polynomial functions. This is kind of connecting to what we did in 4.2. So let's look at example 2, and we have a function, and they gave us one root. Now for this one, when you look at this function can actually be factored. So in order to find our remaining roots, we are going to factor it, and we're going to factor it using the grouping method. And when you factor by grouping, you simply place the first two terms in parentheses and the second two terms in parentheses, and you take out your greatest common factor. So for the first group, I have x cubed plus 3x squared, and my GCF is x squared. So when I take out that x squared, I am left with x plus 3. Because remember, we are dividing both of those terms by x squared. In my second group, I'm going to factor out a positive 25. And when I divide both of those terms by positive 25, again I have x plus 3. So because these are a match, we're going to write our first factor as x plus 3, and our second factor will be the GCFs that we removed. So x squared plus 25. So now we are ready to solve it by setting both of our factors equal to 0. So my first solution would be x equals negative 3. And my second solution, because this is a quadratic factor, when I subtract 25, and I'm taking the square root of a negative, when you take the square root of a negative, we're going to remove the I, or take out the negative 1. And the square root of the square root of negative 1 is I. So our final two answers will be x equals plus and minus 5i. So we already, now they gave us 1, 0. They told us that 1 would be negative 5i. So theoretically, we already knew that we had one that was positive 5i. But we didn't quite know this third one here. So now we have found the remaining zeros. So we have a 0 at x equals -3, x equals +5i, and x equals -5i. So let's do one more where we have to do long division. It's not factorable. Okay, so we have our function here, and they told us that we had a 0 at x equals 3i, which means we also have one at x equals -3i. The only way I can get this factor, if we were to multiply x minus 3i times x plus 3i, we're going to get x squared plus 9. So that is the factor that I'm going to divide into this function. So I'm going to set up my long division. X squared plus 9 is on the outside. And then I have x to the 4th plus x cubed. I'm just writing my entire function. So, long division. When you do long division, you start off by dividing your leading coefficients. You're going to take the x to the 4th and divide it by x squared. So we have x to the 4th and divide it by x squared. We will always divide by x squared. That does not change. And that gives us x squared. Because I like to write things in a certain order, I'm just going to put that above the quadratic term so my x squareds are lined up. Step number 2 is take that x squared and multiply it by x squared plus 9. So I'm going to distribute that and line up your coefficients. So that gives us x to the 4th plus 9x squared. And notice that I'm lining it right under its like term. And now we need to subtract that. So I'm going to take both of my terms and change the sign. So this one will become a minus, and this one becomes a minus. This cancels. So I'm going to bring down my x cubed now. And I'm going to add my like terms. And I'm ready to repeat. So this time I'm going to divide x cubed by x squared. And that gives me x. And then I'm going to take that x and multiply it again by x squared plus 9. Line up your like terms. So that gives you x to the 3rd and 9x. Put that 9x under its like term, which is right here. And we have to change our signs again because we're subtracting. This is going to cancel out. And then we're going to carry down one more rotation here. So the -2x squared is going to fall down. And so will this -18. And we're going to divide one more time. When we divide this time, we have -2x squared divided by x squared, which gives us -2. That goes on the top. And then we take -2 and multiply it by x squared plus 9. So that gives us -2x squared minus 18. I'm going to line it up. Now remember, we're subtracting. So when you subtract the negative, it changes to addition. So both of these change to positive, and we have a remainder of 0. Going back to 4.2, we learned that if the remainder is 0, that means that whatever we're dividing into it is a factor. So now we just need to factor or use a quadratic formula to find our last 2 roots. So when I factor that, I have x squared plus x minus 2 equals 0. That factors down to x plus 2 and x minus 1. So my zeros are, I have 1 at -2, 0, 1 at +1, 0, and then I have 2 imaginary. I have 1 at x equals +3i, and remember there's always 1 with the conjugate because imaginaries never travel alone, so there would be 1 at -3i also. And then we have found all of the remaining roots for that function.